Today, we are going to talk about our Capstone project, the smart supermarket system. While e-commerce has seen great growth over the past decade, in-person supermarket shopping remains an important part of our daily lives. Recommender systems, both in retail and on social media, have become increasingly important for their ability to predict user preferences and enhance overall profits. Motivated by these insights, we have developed a hybrid recommender system. By integrating computer vision and machine learning algorithms, our system aims to not only enhance customer satisfaction, but also increase sales in supermarkets. We have identified a key research problem. Traditional recommenders focus primarily on customers' past purchase history and product proximity to expiration, which often leads to suggestions that do not meet current needs. To improve the accuracy and relevance of these recommendations, our project develops a recommender system that considers not just the user's historical purchases, but also their current mood and the shelf life of products. By doing so, we ensure our recommendations are both timely and appropriate, helping to boost sales and reduce food waste. Our project is structured into 4 components. First, a computer vision system for face and mood recognition. Second, a machine learning-based hybrid recommender system consists of collaborative filtering and content-based filtering. Third, a mapping between food and mood to suggest foods based on emotions. And fourth, a recommendation system promoting near expiry items.
Next, let me introduce you the algorithms we used in our project. This is the workflow of our project. The first part is user login. After user login, we use CV to do face identification and mood detection to get current emotion. The following is the most important part, recommendation. We first get initial recommendation list from collaborative filtering model and then derive current emotion-related products and close to expiration products from initial recommendations using content-based filtering model. Finally, we combine these 3 product lists to finalize the recommendation products. As the diagram shows, we mainly use collaborative filtering and content-based filtering algorithms in our project. Let me explain how we utilize these algorithms to make recommendations. Let's dive into collaborative filtering algorithm first. The key component of this algorithm is matrix factorization. It is a technique to decompose a matrix into a product of 2 or more matrices, revealing latent factors underlying the interactions between entities. We build this user product matrix that includes user ID, product ID, and purchase count, representing how many times each user has purchased each product. And then based on this matrix, we implemented matrix factorization using AOS and SVD model. And then we compare the results of these 2 models and chose the former one. For detailed comparison, my teammate will introduce to you later. Next, let me explain how we implement content-based filtering mode algorithms. We first build up a user preference matrix by calculating the purchase count for each aisle and each department for each user. This involves analyzing the purchase history to determine how frequently a user buys from specific aisles and departments. And then we build up a product feature matrix by computing the average purchase count and setting up binary indicators for each product to signify its association with various aisles and departments. A value of 1 indicates that a product belongs to a specific aisle or department. And get these 2 metrics propelled, we can implement content-based filtering model using neural network. And have collaborative filtering model and the content-based filtering model ready, we are able to obtain user embeddings and product embeddings from these models. These embeddings capture latent factors representing user preferences and product characteristics. and the dot product of the user and product embeddings from the collaborative filtering model indicates users' willingness to buy a specific product. We can also get product similarities by calculating the distance of product embeddings from the content-based filtering model. You may ask, why not use product embeddings from collaborative filtering? This is because content-based filtering model leverages actual product information, such as product aisles and the departments, to generate embeddings. These embeddings are directly informed by the product's real-world characteristics, resulting in more accurate and relevant product similarities.
Now I will introduce our simulation setup, including the datasets we use and how we handle them. We have 3 datasets. First is the Instacart Market Basket Analysis. To prepare the data for model training and testing, we process the dataset to get the purchase count for each user and each product. The second dataset also originates from the Instacart. We call it Mood Food Mapping. Our literature review on the impact of emotions on eating behaviors suggests that positive emotions promote the intake of nutritious and healthy foods, while negative emotions often encourage people to buy foods high in sugar, salt, or fat. So we apply these findings to categorize the supermarket products, reorganizing them by their aisle ID. This mood-based data will be passed to our recommendation system. The third dataset is products with expiration dates. Since the original data does not include product expiration dates and acquiring public data is challenging, we decided to set a certain proportion of nil expiration products in our dataset. Based on referencing supermarket disposal rate, we assign expiration dates to these proportions of products. This will allow us to filter out close to expiry products effectively. Our system is implemented in a program environment consists of 3 parts. First, for face recognition and emotion detection, we use deepfakes, which provides robust and reliable performance. Second, our recommendation system uses scikit-learn for collaborative filtering and TensorFlow for neural network-based content filtering, offering powerful recommendation capabilities. Third, our web app is built with Python and Flask on the backend, offering a lightweight framework. The front end is developed using React, providing a responsive UI, and we use Firebase to store the user information. These choices make our system efficient, user-friendly, and seamlessly integrated. Additionally, we use an external API for real-time product search, which retrieves product images and simulates prices and discounts, making the app experience closer to shopping in a supermarket. In our web application, users have 2 pathways, one for new users and one for existing users. New users sign up by providing username and a profile picture, which is saved in Firebase and used for facial recognition. During login, the system recognizes the user and records their mood. After logging in, users complete a preference survey, selecting from the top 50 product aisles to tailor their recommendations. The system then generates personalized recommendations based on their interests and detected mood, including initial mood-related and close to expiration product suggestions. Existing users log in by uploading a photo or using the app's camera, which is matched with stored images in Firebase for identification. The system also detects their current mood to tailor recommendations. After logging in, users go to the Get Recommendations page. This system then generates a list of personalized recommendations based on their historical purchase data, current mood, and items close to expiration, promoting both personalization and sustainability. Additionally, users can view their purchase history below the recommendation list to evaluate how relevant the system's suggestions are to their past purchases.
Okay, let's dive into our result part. Our face recognition
and the emotion detection functionality powered by DeepFace. DeepFace is known for its high accuracy, which is over 97% in identifying faces and understanding emotions on the labeled faces in the world dataset. Moving on to our machine learning models, we compare the three collaborative filtering approach, the baseline model, SVD, and ALS. The formulas on the right are how we calculate these metrics. In order to provide a simple benchmark, we define a baseline matrix. We use the popularity-based approach to measure baseline position, recall, and F1 score. As you can see in the table, the ALS model outperformed the others significantly. It achieved a position of 1.89%, recall of 4.19%, and an F1 score of 2.26%. While these numbers might seem low at first glance, they represent a substantial improvement over the baseline and the SVD models, especially considering our large and diverse product catalog. We also evaluate product similarity comparison between our content-based filtering and the ALS model. The comparison of finding similar products shows that the content-based filtering model significantly outperforms the ALS model. Our workflow use ALS for initial recommendations and then use content-based filtering for refined recommendations. By considering product features, user emotions, and the expiration date, this hybrid approach leverages the strengths of both methods for comprehensive recommendations. We also design a feedback survey to evaluate our front-end web app. Our user survey shows an encouraging result. Nearly 80% of users rated our system 4 or higher score out of 5. Over 90% said our recommendation affects their buying choices, with 78% more likely to buy recommended items. These results show our system works well and help users make positively impacts on their behavior. We also collected some valuable suggestions through the survey for our future improvements.
Limitation and future work. We have identified 3 major limitations of our project. The first is the assumption underlying the computer vision component. Although our program can handle multi-face situations, it performs best when there's only one person present, viewed from the front, with prominent facial expressions. To address this, one potential solution is to transition from analyzing still images to processing video clips to improve detection accuracy. The second limitation lies in the recommendation logic. The recommendation system we built is static, meaning it cannot incorporate real-time user feedback or adapt to evolving user preferences over time. In future work, another area of focus is making the recommendation system dynamic by allowing users to provide live feedback, such as liking or disliking recommended products. This would enable the system to further adapt and to improve. As my teammates mentioned earlier, due to dataset limitations, our system currently only takes expiration dates into account to reduce food waste. It lacks integration with real-time inventory, market demand analysis, and the study of the prices and discount relationship. If we were provided with this missing information, we could further enhance our model by introducing dynamic pricing. In conclusion, our research advances machine learning-based supermarket recommendation systems, offering a more dynamic and personalized shopping experience. This approach not only caters to customer preferences, but also promotes sustainability through effective management of expiring products. Thank you for your time. Please feel free to reach out if you have any questions.